In this new episode, we're going to look at the synchronization mechanism that happen in a real-time operating system. Synchronization is required to guarantee all the pre-requirements for a task. You want to compute only on valid data, as well as protecting critical resources in order to not corrupt data. For example, if you are accessing the same type of data in two tasks, you want to make sure you're not writing and changing the values and being stuck all in the middle. Same goes for hardware resources such as an I2C communication. When you started to write something inside of the I2C, you don't want to be stopped and start putting some other data that would corrupt the complete transmission. There are several mechanisms. We're going to look at the two most important ones, semaphores and mutexes in particular. I'd like also to talk about critical sections. Critical sections are code sections whose integrity should be guaranteed by restricting exclusive accesses. Again, for example, if you're accessing some very specific hardware resource, programming a DMA, for example, and you don't want someone to stop you right in the middle. This will have to be guaranteed by semaphores, and semaphores will be used to avoid two tasks to access a specific resource at the same time, or also by specific hardware locking mechanisms such as disabling the interrupt. If you're disabling all interrupts, the operating system will not be able to take control over the processor anymore, and that way you will not be disturbed in the sequence of operation you want or you consider to be critical for your hardware mechanism, for your hardware block. Semaphores. The notion of a semaphore is a concept that is borrowed from railway. You are going to wait until you are given permission to move forward. And how does that work? It works with a variable that will save some tokens. Tokens being an incremented value. Every time you want to pass through, you have to take one of those tokens and decrease the value in the semaphore. If the value is 0 or negative, you cannot go through, and someone will have to increment the specific memory location to let you go through. So here's an example. You had this variable. You took your the value from the task, so you cannot actually do something. So in this particular case, task on the right is blocked. The interrupt on the left decides to put a token on this variable that will, as a matter of fact, unlock the other task, allowing the code to go through. And now, with this kind of mechanism, that brings another concept we have not looked into yet when it goes to software flows, which is the combination of real-time operating system and an interrupt-driven scheme. Now, as you can see, you can still have all your hardware ISRs that will now create tokens to unlock the various processes. So the operating system will still deal with all the scheduling and whatnot, but that will be triggered by the hardware requests. And that is one of the best systems you can implement to guarantee complete operation on your system and so on and so forth. I'd like now to review mutexes. The concept of a mutex or mutex comes from mutual exclusion. Mutexes are used to protect shared resources, a specific memory location or a piece of hardware. So in that particular case, you have some guarded resource, and task A is going to make a request to that and take the token. Task B is blocked because the token is not available anymore. When task A is done with this guarded resource, it will release the token, and task B will be able to go through. So a mutex is basically a semaphore where you have a single token. It's like accessing the restrooms with having a single key. Only a single person can go there at a time. Fairly simple analogy to understand. Now, you'll be able to indeed synchronize your various processes, but you also need to communicate and exchange data between your the various parts of your system. And data can be exchanged between tasks using various mechanisms such as queues, pipes, shared memories, and so on and so forth. I'll talk very quickly about shared memories. It's basically a portion of memory where you have a pointer to access to that, and this pointer is protected by a mutex. So only a single person at a time can go to the shared memory and modify it. Simple. On an operating system, data are, as I said, usually exchanged using pointers. It's done to avoid long and useless data copy. And the pointer validity needs to be guaranteed that the concept of shared memories. And to do that, as I said, you can block your stuff. However, there are queues that can be used. So the concept of a queue is that data is generated by a task, but there is no guarantee that this task will be processed immediately by the other task. So you want to create some sort of a buffer. So you create an asynchronous data generation and data consumption. Task A will generate data, store that inside of the queue, and task B will take this data and consume it when it has some available CPU time. So now, can we always use an operating system in an embedded system? Well, it will depend on the performance of the operating system and what your CPU has. For example, on an 8-bit CPU, it's going to be hard. On a 32-bit plus CPU, it is, however, recommended depending on what you have to do. You obviously have to consider the flash memory requirements. Things can be very light, only a few kilobytes of information for the kernel, or larger, 250K for the kernel. Obviously, you can see that embedded systems, operating systems, are not as big as what you'll have on Windows or macOS. They are much lighter, so consider that also. You have a much lighter set of capabilities. You also have to consider the RAM requirements. You need to have enough RAM for the stacks, for all your tasks, the RAM for the kernel, and so on and so forth. So everything dictated between the complexity of your application and the capabilities of your hardware.